Hi guys, and welcome to the video on esterification. In this video I want to have a little bit of a look at the process of esterification, the one that you've carried out now in the laboratory, and also to have a look at the procedure in terms of refluxing and why that procedure is necessary. In order for us to do that, we need to understand what esterification is. And esterification is a process that is a chemical reaction in order to produce an ester. Now we know that an ester is an organic compound which is formed from the reaction between an alcohol and an alkanoic acid. The problem with this particular reaction is it's very slow and it does not proceed all the way through to completion. It's an equilibrium. And because it's an equilibrium reaction, we do not get the reaction going through to completion. That means there's a couple of factors that we need to consider in order to make sure that we maximize the yield. So, what are the challenges then associated with the process of esterification? Well, we have a few issues. Slow reaction at room temperature. The fact that it's in equilibrium, that is a reversible reaction, and therefore it's not going to go to completion. As I mentioned in the previous slide, it's an equilibrium. We also have a problem with the fact that both the reactants and the organic products are volatile. They quickly move from the liquid into the gas phase, and you'll know that because you could smell them in the lab. And finally, the liquids themselves, most of the liquids, not so much the acid, but certainly the alcohol and the ester, both the liquids and the vapors may be flammable. And therefore, we have an issue with naked flames. So therefore, our procedure for carrying out esterification has to deal with the slow reaction at room temperature. So this is going to involve the addition of heat. It's a reversible reaction, so therefore we're going to have to set certain conditions which favor the formation of the product. The volatility means we want to try and make sure we cycle the materials so that we can continue to ensure that we don't lose too much of our reactants. And then finally, we need to think about the source of our heat that's not going to bring potentially flammable vapors in contact with a naked flame. The solution is refluxing. Refluxing is a chemical process in which we place a vertical condenser over the top of our reaction vessel. Now, refluxing isn't just about the vertical condenser. It's also about heat. We need to make sure that we are adding heat to the solution. But the problem that we have with heat is we have to make sure that we regulate and control the heat. So in order to do that, we either use a water bath, which is what you used, or we use some sort of heating mantle, something that we can rest our reaction flask in order for this reaction to occur. Because it's a slow reaction, it's often easiest to allow this reaction to occur over several hours or perhaps even days, if that is practical. And that will maximize the yield. The use of the vertical condenser allows vapors, as they move up through the column, to be cooled with the water that's circulating through the condenser, and therefore to condense and drip back into our reaction vessel. As they drip back into that reaction vessel, we avoid too much loss of our reactants. Because we're producing a lot of gases as we heat the mixture, we want to make sure that the system remains reasonably open. And we either do that, we've stopped it and we release that regularly, or we put a thermometer at the top, or else in some cases it's just left open. So the open system negates the pressure buildup. So the gases will continue to build pressure inside of the column, and so we want to make sure that we are able to release that pressure. And of course, an open system doesn't allow that pressure to build up. We also don't want the vapors that are forming in the reaction vessel to be bubbling too violently. The use of ceramic boiling chips helps to provide an additional surface area for those bubbles to form and then for them to be released from the reaction vessel. We don't want to use marble chips. The problem with marble chips is the marble is calcium carbonate and it will react with the acid. It'll react with the acid, and if it reacts with the acid, then we'll have carbon dioxide gas being produced and we'll have our acid being neutralized, and that will actually shift our equilibrium back in the wrong direction. So we don't want that. So each of the conditions that are part of refluxing is designed simply to allow us to recognize that we have an equilibrium, to maximize the yield, and to ensure safe conditions for the carrying out of this process. Now, one other important consideration which I haven't looked up at here is that often one reactant is in excess. And again, that higher concentration of that particular reactant pushes the reaction forward and allows us to continue to maximize the yield of the product that is, in this case, the ester that we're trying to form. The final thing that we do when we're looking at the process of esterification is we want to add a sulfuric acid catalyst. Now, the catalyst does not change the position of the equilibrium. It does not change our yield at equilibrium, but what it does do is it allows us to reach that position much quicker. The important thing when you're writing about this particular step is that you need to make sure that you talk about concentrated sulfuric acid, very highly concentrated sulfuric acid, because this is going to act as a dehydrating agent. That is, it's going to attack the water molecules. When we are reacting our alcohol plus our acid to produce our ester plus water, it's the catalyst that is going to be sitting over the top, but is actually going to be withdrawing the water, dropping the concentration of the water or the relative amount of the water compared to the ester, and therefore that is going to drive the reaction towards the right and increase the concentration of the ester. And that is why we choose to use the sulfuric acid catalyst. So here's a question from a few years back, 2007, question 23. This was a 3-mark question. When hexanoic acid and ethanol are mixed together under certain conditions, esterification occurs. Describe the conditions necessary for this reaction and give the structural formula and names of the products. Two products. Okay, the structural formula and the names of the products. We know one of these products is water. Okay, that's a pretty easy structural formula. But what's the other product? Well, the other product is the ester. And the ester is going to be, the name of the ester is going to be what we get when we get hexanoic acid and ethanol mixed together. Now, the acid is the one that produces the anoate ion. So it's the second half of the name for the ester, which means that the alcohol provides the first part of the name. So our ester is going to be ethyl hexanoate. That's its name. What does it look like? Well, if you look at where the acid group is, the acid group is going to have to link to where the 6 carbons are. So the double bonded oxygen is the important one here. So we've got 1, 2, 3, 4, 5, 6 in this direction, and then eth is 2, so just 2 in this direction. I'm going to put all these little bonds here. I won't put hydrogens around them. You will make sure that you do. There's hydrogens around each of these. So we've got the structural formula and the names of the products. What we haven't done is describe the conditions. So we need to describe the conditions necessary for esterification. Well, we need to heat because the reaction is too slow at room temperature. We need to reflux. We need to add a vertical condenser over the top of the reaction vessel. This allows the volatiles to cycle, condense, and drip back down into our reactant vessel. We need to add a catalyst. So the catalyst that we're going to add is going to be sulfuric acid, and make sure you identify that it's concentrated conc sulfuric acid. We're also going to control our heat, and we're going to add boiling chips, and these will be ceramic boiling chips. Both of the boiling chips and the heat are going to allow us to regulate the temperature as we're heating to make sure that we don't have any explosions of volatiles, and also that we don't have any flames as a consequence of the flammability of some of the both products and reactants in this particular reaction. How did you go?